going about it all wrong. Actually, yeah, so we can't actually prove this without proving A part first. So, you know, I was getting distracted. So yeah, let's directly prove that this is a convergent sum, right? And one standard, the definition of some series converging is if the partial sums converge, right? So first I'll show that it's increasing and then it's bounded, and that's a standard fact that shows that it's going to be convergent. So I think all of the standard facts I'm going to use are going to be proved later. So yeah. Okay, now this is shown. Okay, yeah. Okay, so what is this exactly? This is equal to, so if we take the partial sum here, we have x dot y, but we're taking the nth vector here, right? And this is less than the norm product, right? Okay. So if we show each partial sum is bounded, then we're done. And that's pretty easy to do. So we just square it. And we note that the square is going to be, so let's call it x and let's call it y. So this is the sum for each series, right? Yeah. So this is actually going to be x less than x squared dot y squared. And that's because we're, or is it just x? Yeah, just x. So that's because we're summing all the squares, right? That's the definition of what the norm is. And we're summing all of the parts here, and we're removing infinitely many positive terms here. And they're all positive, so that's why the inequality holds. Yeah. So, okay, now this is a finite, this is going to be a finite number no matter what, because this is a finite number, this is a finite number, right? And because of that, every partial sum is going to be bounded. So that means the entire sum is, while increasing, because we're adding positive terms again, is going to be convergent. So yeah. Okay, now that we have that, we can easily prove that x plus y belongs to x, or in other words, summation I is equal to 1 to infinity xi plus yi whole square is convergent, right? Another way of writing it. It's a real number is the point actually. So yeah, and we are free to expand, work algebraically on these things. That's another standard fact, I guess. So this is perfectly valid. So yeah, these get multiplied because, oh yeah, not quite. Yeah. So note that if mod of xi yi converges, then so does xi yi. That's another standard fact. And note that the scalars can come out and inside as you wish. So this is equal to x plus y plus uh, 2c, and c will be c is less than x dot y, right? Equal. Yeah. So because of that, it's a finite number, and yeah, the sums, if you add convergent series like that, you'll be fine. So x x being convergent, the series x being convergent, and y being convergent implies x plus y is convergent. That's a fact you can use anywhere. Yeah, maybe that's what we'll also end up proving. So yeah, I'm using a lot of standard facts there, but I think section 21 handles all of them, so it should be fine. Yeah, Cx. Same thing here. We can take the constant in and out of the sum. So if we multiply it by C here, it can be outside. So the sum will end up being Cx, and since C is a finite number, we're fine. And note that we just proved that, yeah, the axioms, that any member of X is, oh, bad notation, sorry about that. So any member of X is satisfying the three axioms of question 9, and I think those are the axioms of the of a vector space. So yeah, we're essentially proving that any vector space can give you a metric space, and that's true. We can get a norm from it, and that norm is precisely going to be our. So yes, x plus y belongs to x, right? Cx belongs to x. Now we just have to show that x dot y belongs to x. But x dot y is a finite number, so it's x dot y is defined as something. That's not really an axiom, just a definition. We're going to work with this now. Okay, now show that this is a well-defined metric. Okay, so now we just have to show that the norm. So how do we have the norm here? Yeah, we have the metric defined here, d of x comma y. Hmm. Okay, so norm of x is equal to d of x comma 0 is equal to sigma I into 1 to infinity x I square root, right? So yeah, if we define the norm this way, and yeah, there is a direct correspondence between the two, then yeah, then a norm of x minus y is equal to d of comma y, x comma y, right? You can check that easily. Of course, these are vectors, but you get the idea. I may have missed the vector sign a couple of times, but I think you get it. So yeah, note that we were working in an arbitrary space. While it wasn't infinite dimensional, it doesn't really matter here. So yeah, the whole point is if we have a norm on a vector space, then we can get a metric. And this is a norm, but I'm still going to proceed as if we don't have the general theorem ready yet. So yeah, it's the same logic here. Let's see, x minus y. So if we show that norm of x plus y is less than equal to norm of x plus norm of y, then we're done, right? From the same way we did it earlier. So how would we do it? Let's see. Oh yeah, we proceed in the same way. Yeah. We just showed that the sum of the norm, actually the norm is the sum. The So first of all, x dot y belongs to x. No, not x to. Hang on. Yeah, norm of x actually, yeah, mod of x dot y is less than or equal to norm x dot norm y, and it's a finite quantity, and it's finite. It's determined by that. That's exactly what we use to prove this inequality in the same way. So I'm not really doing it again. So yeah, we just everything in the previous question holds here is the point, because it was all the proofs only rely on the axioms, not really the nothing. It had nothing to do with the fact that it was Rn. We were just using those three axioms. So yeah, and yeah, so it's a well-defined metric. Same thing for a norm. We For a general norm we get three conditions trivially satisfied: the equal one and the symmetric one. Norms are also always symmetric because the square is symmetric. I think in the in the cube. So yeah, we can have that for a general P. So this can be a P, and I think when P is odd, we mod it to be safe. I'm not sure, but yeah. Okay, let's solve question 8. Another question I spent far too long on, but it was a nice question, that's for sure. Yeah. You might notice a lot of cuts in this videos and in this video, and that's because this topic was personally quite hard for me, and I think it is one. And yeah, it should be done thoroughly, anyways. Okay, so now that I've shown that this formula defines a metric on X, now we can, I won't have any hesitation on proceeding with question 8. And from the metric, we can get a metric topology, which is called the L2 topology. I'm not going to pronounce the little l. Not the little is just their L2 topology. I hope there's no such thing as an L2 topology. I hope there isn't. I might be surprised. Yeah. So first we show that any open, these are final. So let's prove L2 is finer than U first. Yeah. So observe that any open set will be of the form uniform. Right? Yeah. Any open set will be of the form U intersection X. So, we're taking a subspace topology here. And why that matters is because X is not really a nice looking set because you can have, okay, so you want a convergent sum, right? That's what matters ultimately. So you can have zeros everywhere and then some finite number anywhere at one place or even finitely many places and then zeros everywhere. And what ends up happening is this can move on anywhere. So what that means is, yeah, the set X is not going to behave very nice. And that's why we have the Hilbert cube later. That does behave a lot more nice. So any open set will be of the form U, which is open in R omega, and X intersection X, which is the set we have defined. So yeah. So let's take any arbitrary vector X and take a neighborhood U around it. Now, if we show that any neighborhood in the uniform topology is also in the L2 topology, then we're done, right? Okay, so let's say any open set here is going to be having a basis of this form. So yeah, we're using theorem 13.3. Any basis will have a basis containing it, right? Actually, what am I doing? Yeah, that's not the way to do it. Hang on. So since both of them are actually metrizable, they have a metric topology, a metric. So yeah, they are both metrizable. I'll just directly use the metric space theorem, that one. Open ball inside an open. Yeah. So we take any basis element, B rho bar X epsilon, right? Yeah. Now is B, I'm going to call it L2, X bar epsilon a subset or a superset? If not, can we find a smaller number? Right? That's what we really want. Okay. So if the sum deviates by epsilon, the value at each point must deviate by less than epsilon. Unless it's less greater than one, but it won't be greater than one, right? That should be fine. So if it's less than one. So small details, there's a bit of a small detail to work around with, but I think it's fine. It's possible. I'll work it out on the board and then explain it. Yeah, so I was slightly wrong, but it's actually square root of epsilon. But yeah, if you vary by square root of epsilon, the square and actually I might just be epsilon. Either way, yeah, square root of epsilon definitely works because it's smaller than. Oh yeah, square root of epsilon is bigger than epsilon, right? If it's less than one. So yeah, just take epsilon itself. Yeah, so change by epsilon, it's squaring it, so that error does get bigger. Yeah, and then you square root it back. So uh, the worst case scenario, what happens is that yeah, you never go beyond epsilon. So if you have to stay within a band, and we're looking at all the sequences that such that the sum doesn't vary by more than epsilon, to ensure that happens, it has to remain in the band. So yeah, it's actually contained. And because of that, by that criteria, the L2 topology is finer than the uniform topology. And the box topology is trivially finer than the L2 topology because any open set you can think of, it classifies as, yeah. So actually, yeah, just, no, that won't work. Yeah. For any basis element of this form, you can find a box element that's contained in it completely. Simply, yeah. So yeah, just take epsilon by 120 if you want, and you can contain it in almost seven. It will be fine. So yeah, the box topology is finer than every topology in R omega. You can think it might actually be the finest one. That's probably an overstatement because there can be some ridiculous one, but any normal one you can think of, yeah, the box topology would be finer than it. Okay, so wait. Oh, we haven't attempted question seven, have we? No, question five. Yeah, we haven't attempted question five. I'll attempt it after this. Yeah, I hope I don't forget. Anyway, the answer to question five is set of all convergent sequences. Essentially, it just, yeah, I'm distracted, whatever. Yeah. So you take the neighborhoods around omega or around the point zero, the vector zero, and you take any band here, and any convergent sequence is going to be essentially in the closure, right? So you take the point zero, all zeros, or even any point neighborhood around any point that's eventually zero, doesn't matter. What will end up happening is that you can get a convergent sequence around. So the fact that it's convergent will help us be contained in the neighborhood around the infinite points that are zero. And for the other ones, we just take the right sequence that is not zero. So the finite points before that, the convergence is fine. It's so infinitely many points are in the epsilon band because it's convergent. That's what the definition of convergence means. It will slip in into the neighborhood. So yeah, essentially, we have the band, which is a neighborhood, and we want to slip, yeah. So it's going to be between R infinity and R because the product topology has R as the closure. So yeah, every convergence sequence falls in because for these points, we can just take any, we can take a sequence that's, infin- uh, infinite in all but finitely many points. Sorry, non-zero in all but finitely many points. It was zero in all but finitely many points. And for the other ones, we can take the neighborhood and exploit that. So yeah, that's the answer to question five. Yep, I guess that's the answer. I'm not doing it. But yeah, for this one, so let R infinity be all the sequences that are eventually zero. Show that the four topologies that are infinity inherits as a subspace of X are all distinct. So first of all, note that R infinity is a pure proper subset of X. I'm not proving the proper one that there exists some counterexample. Actually, 1 by n. Yeah, 1 by n is a good counterexample. The sum 1 by n square, I'll link a video, I think, is equal to pi square by 6. So it's convergent. There are many proofs of it. I'll show you the one I first watched back when I was learning. And yeah, that's an example of a set that's in X but not in R infinity. And it's a convergent one because if it's eventually zero, then we only have to add up finite terms, and that means it's going to be convergent. Its squares are also going to be cubes, fourth power, anything you take will be convergent. Partial sums, partial sequences are always, they're going to be a real number. Partial sums, yeah, right. They may or may not converge. That's what we really want. Anyway, so now we have the subspace from this metric. So we have a metric topology and then a subspace on R infinity. Okay. So this is actually easier to do because it's the product topology. How would that look like? So yeah, now we have to show that the box topology is finer than the L2 topology, which is finer than, so strictly finer than the uniform topology, which is strictly finer than the, hang on, yeah, than the product topology. So note that this fineness, the fineness order already exists. We have proven it. We're just trying to generate counterexamples. So we want the strictly finer thing to happen. So we want a neighborhood in the uniform topology that's not in the product, and we have to go that way for all steps. Okay. So let's take an epsilon band around the neighborhood of zero. So zero belongs to the zero. The vector that's zero at all points is going to belong to R infinity, so we're completely fine. And let's see. Yeah. So is this in the product topology? That's probably no. Yeah, it's no because at some point it has to be infinite, right? So at some point it has to contain the entirety of R infinity. And yeah, I'll think of it better. Okay. So first, a bit of intuition. Any open set here would be containing a basis which would intersect R infinity. And how would that look like? So let's say we have an epsilon band because that's what all bases are. Bases look like. And yeah, essentially we'll take a member R infinity and it would lie in the, yeah, it would lie in the band and then it would start being zero after a point, right? That's how any point would look like. And essentially you'll get all finite sequences that lie in the band. But with the product topology, however, yeah, it will stop at some finite point. So after a while, it would so it wouldn't be contained in the band anymore after a certain point. It would go nuts essentially. Yeah. So now I just have to show that this band cannot lie in the product topology, or and there's no basis element of the product topology that would lie in it. So yeah, essentially that covers the almost the entire proof. At some point, the epsilon becomes less than 1 by n, and that means it contains the entire space, and yeah, it escapes outward. So there's no product topology basis element that can be contained inside the epsilon band, and that's yeah why it's so strict. So there doesn't exist the p x epsilon, yeah, contained in the rho bar. Yeah, that's essentially the how we have to prove it for all of them. So you take any arbitrary epsilon band here and or any arbitrary basis element, and you show that whatever element you take, it's not going to be contained in it. So in this case, it's going to expand and blow up to R after some point. Yeah, no matter what you take, but it has to be contained everywhere if we're taking a uniform topology element. So this one's done. Yeah, now let's do this one. So here, well, yeah. So if you take a element here, how would it look like? So any open set in the L2 topology, it would essentially, yeah, have sequences that don't divert, don't go beyond. Actually, yeah. So note that we just need a single element. The x can be fixed. The x doesn't need to be arbitrary for this to work because we just have to show that it's not the finer, right? Not finer is enough. So x in this case will be the zero vector, and we can work with just that. Yes. So if we consider BL2 0 epsilon, it contains all the sequences that are less than essentially their sum is less than epsilon, right? The sequence is root square sum, squares root. So yeah, So that means it can actually contain points that are exactly epsilon at only one point, and it can go in anywhere, right? But the epsilon band is containing more than that. It's not contained in it, right? And any band that's actually contained in it will what? Any yeah. So there cannot be any band contained in it. Is that it? Yeah. Right. So if you try to take any band, what's going to end up happening? Yeah, you can always take a small enough sequence that adds up to you know epsilon. So if the trivial examples include epsilon by 2 to the power n, so that adds up to epsilon by 2, right? So you can always find a smaller sequence that the band can't contain. So yeah, I'll think of a better explanation. That's a pretty close one, but I'm not satisfied with it. Hang on. Yeah, so I was right to not be convinced by that explanation. There's a far better one, and I quite like it. So first, I'll restate the problem. So let there be any delta band, right, around zero, and I'll show that there exists a member for every delta band you think of, such that its square sum is outside epsilon, so it's more than epsilon. So how do we find such a thing? It's quite nice. So let's take delta by 2, right? So that's going to be less than delta. It's inside the band, so it's all fine. So you take finitely many m. So you take finitely many elements such that it's less than epsilon, but yeah, it's less than epsilon, but yeah, it's less than epsilon, but it should like essentially you want to grow and then you want to stop the growth at some point. So the choice of m will be elaborated on later. So let's just go with it. Choose an m such that delta by 2 m is less than epsilon. Yeah, but actually we can take an m such that delta by 2 m plus 1 is greater than epsilon. So let's take that, right? Okay. Now after some point, so we already have m, right? And we also know that the sum 1 by n square is convergent. So it's equal to m pi square by 6, right? So we always have some number n such that the tail is less than epsilon for whatever we want, right? The tail always shrinks, and we're going to exploit precisely that. So there exists an n such that so I'm also assuming epsilon is less than pi square by 6 because if it's more than pi square by 6, we can we have. I mean, we just need one epsilon example, right? So just let's take a small enough value so that we can actually play around with the stuff. But yeah, if it's pi square by 6, we might actually have to scale. Yeah, ultimately, we can still use the same argument, but we'll have to scale it. But yeah, so we have an m such that it's less than epsilon if you take this, and more than epsilon such that it's, yeah. And so we can choose an n such that its tail is going to be, yeah, more than epsilon. We can always choose that, I think. Hang on. Mm, or do we just want to go the divergent route? We could possibly go that way too. But yeah, essentially we get a decreasing function such that its sum is actually yeah, we could just get a decreasing sum such that it's divergent completely. That also might work. Oh yeah, what am I doing? Yeah, this example is nice because it goes into the insight of what. Okay, does it explain the Riemann rearrangement theorem? Probably not, but it does give you a big better intuition about infinite series. But you don't need to do any of this. So just take 1 by n, right? Or 1 by root n, at some, this is decreasing enough, so at some point it's going to be less than delta. So once it's less than delta, you just take all of those numbers, and before that you take it to be zero. And the whole point is its series sum is infinite because summation 1 by n diverges. So yeah, you can exploit that, and essentially there is no delta band that can be contained in L2. Okay, the reason I avoided that was because it wouldn't be a member of X anymore. So yeah, hang on, then it could be a problem. Okay, so we can't work with 1 by n. Okay, yeah, let's proceed with our original approach then. Because if it's not convergent, then it's not a part of X, and then the discussion is, irrelevant. Irrelevant. Then yeah. Okay. So, hmm. So how do we work with this? Let's see. Okay. Can we get a sequence such that? Oh, right. We can get any sequence we want. Hmm. Actually, yeah. Yeah, I was prepared. I could just get away with this. Yeah. Okay, so for the first m plus 1 terms, we take delta by 2, and we take choose m such that it's greater than epsilon. So we're already heading towards the outside territory. And then after that, we choose 1 by n. So we choose the n which happens to be less than 1 by delta, and then we carry on from there. So choose this n, and then from after n, m, we just keep on pushing that in. So the sequence would look like something like delta by 2 for the first m plus 1 terms. And then after that, we would have 1 by n and then 1 by n plus 1. This n is, mind you, not has this n has nothing to do with m. It only has to do with delta. And then, yeah, after that, we'd have 1 by n. And the point is, this would converge to something like pi square by 6. This would converge to something, would add up to something greater than epsilon. And this lies in the delta band. So there is no delta band that can contain a sequence being less than epsilon. So yeah, and that shows that it's strictly final, not just final. I hope this example was yeah. So you cannot just use a sequence that diverges because then it won't be a member of X. So it also has to belong to X. So it belongs to X as well as in the delta band. And that example is yeah, what I've written. This is one of the many examples you could think of, and it's not a part of L2. And yeah, okay. Now for the last one, the box topology. So why is it strictly final? Well, you take any sequence. I think. Hmm. So any open neighborhood here is yeah. Can we think of an open neighborhood that's not convergent, right? Or that doesn't have, yeah, right? Okay. So we know that 1 by n would the sequence 1 by n belongs in N2, right? Yeah. Hmm. And its sum is less than pi square by 6. Square sum, right? So how do we work with this? So I think my gut feeling says to choose epsilon equal to pi square by 6. If it's arbitrary, we can scale the whole thing and it doesn't matter much. So any constant works for any this type of argument. Okay. Now, yeah, let me think. Okay, I just realized that we were actually working with R infinity. So that argument still holds, but forget about the 1 by n and just replace it by 0. Yeah. So it has to be a member of R infinity, not X. So yeah, everything else does hold up though. So it's still a member of the delta band. We just take extend it to that point. And yes, that makes me realize how stupid I was being because we just have to work with finite sums, not really infinite ones. So yeah. So we take, how do we show it nothing works? We take any arbitrary box band here, right? And what would that look like? That would be zero at some point, but you still have, so yeah, we have a box band. We don't have a box band, but arbitrary box open set, whatever you want. And you take all functions that are eventually zero and then intersect with them with this topology. So yeah, that's what it would look like. And we have to show that there's no L2 thing, L2 open neighborhood that would cover it. Yeah. So I just have to clarify that we're taking finite cases. So we might as well think there's zero after some point. And yes, so if its sum is going to be less than delta, yeah, so essentially for any delta sum, we just have to make sure we find a box topology that's contained in it, right? Okay, not contained in it, that's not. So yeah, I'm talking to myself. I'll just think about it again. Yeah, so if you take, let's see, pi minus epsilon by 2 to the power n, I think even one is fine here, comma epsilon by 2 to the power n. Yeah, so here I'm going to prove that for every delta ball around zero, it's not going to be contained in this spaces, right? In fact, that's what we have been doing the whole time. So you take, if you can show that there exists an open set, any open set, such that any basis element is not completely contained in it, then it's not final. I'm basically just using theorem 13.3, but in the negative direction. So yeah, that's what we have been doing so far, and that's how you can summarize the entire method of the solution. And yeah, uh, to show that it's not a member, a strict subset, you give an example of a member here which is not in there, right? And that's what I did for the uniform one here and for the product one here. Yeah. So now let's take this one. Here it's quite simple. You just, let's see. So observe that a sequence with all zeros but delta at one point or delta by two at one point is going to be belonging here, right? So I'm going to call it, I wanted to say delta delta because, from the direct delta function, but that's going to be confusing. Okay, it's one here. Okay. So delta epsilon by 2. So it's kind of, the notation is motivated by the Dirac delta function. Yeah. So this belongs here, but it's not going to be. It's going to be outside of this open set, and that's because at some point this epsilon by 2 is going to be bigger than here. So the delta can be at any point, and we're going to choose the point such that epsilon by 2 is bigger than 1 by 2 to the power n. So yeah, and that's the counterexample. So at every point, we need a counterexample for an arbitrary basis element. Yeah. So it's quite similar to showing some space is not, strictly finer or not comparable to another, like RK and RS. So the argumentation is quite similar. Okay, so the good news about the Hilbert cube is that it removes quite a bit of the nonsense, like the function blowing up anyway. And as a result, quite a few of these strict inequalities aren't strict anymore. So let's work with that. Also, yes, the inequalities, so the fineness works in these directions because that's how subspaces work, right? Okay, so this is indeed fine. So let's check that. I initially thought it wasn't fine, but then I got a counterexample. So yeah, let's see. Yeah, so you take any that 1 by 2 to the power n was a pretty good example because what ends up happening is, yeah, you try to take anything, it's going to be outside. It's The example was valid in the Hilbert cube because it was literally a member, it was a subset of it. So nothing really changed. The argument still holds here. Uh, I'll just check it. Does anything change? So L2 will be of the form that, yeah, it doesn't change. It's completely fine. Now L2 and U, however, are the same tuples. And how do we show that? Let's see. So we have to show that for an epsilon ball here, so I'm going to take 0, but yeah, we have to do it for an arbitrary case. So yeah, sorry. That we can always find a smaller ball that's contained here, right? Yeah. Yeah, so I'm going to take a shortcut and prove that the L2 topology in the Hilbert cube is the same as the product topology. And what that does is show that the uniform topology is also the same as the product topology through a shortcut, what I like to call set theoretics and with you. So, P is containing U containing P, so that's that way. Yeah, so how do we do it? So observe that the fact, yeah, any epsilon ball around any point, it doesn't have to be 0. Well, since 1 by n is such that 1 by n square is convergent, right? Its terms is squares is some are convergent. So because of that, what ends up happening is if you take a late enough tail, so you take the tail that's far away enough, so there exists an n such that for all n greater than equal to n, um, summation one an is less than epsilon for all epsilon. Yeah, pretty much. In this case, square because we're taking the squares to be convergent, but yeah. So there exists an n. There always exists a finite n such that for all later terms, the sum of the tail is less than whatever value you want, right? So for that value, you'll work with that. So what does this help us with? This helps us with the fact that after a certain point, we're going to have the entire tail fill up. So what does that mean? Well, because the difference is going to be less than 1 by n, which means their the square of their difference is going to be less than or equal to 1 by n square. Uh, Essentially, for an epsilon neighborhood, after some point, you can take any point in that 1 by n comma 0 square. So you can choose any point from here as long as it's after n. And what does that mean? That means it's the entire set after a certain point, and before that, which contains finitely many terms, it can be whatever you want. And this probably sounds familiar, and that's exactly what the product topology is. So yeah. And of course, it extends to the epsilon band as well, because after some point, the 1 by n, is completely contained by it. So yeah, all three of these topologies are equal. And if you want, you can play around with LP topologies in general, but I'm not doing that here. I think LP, in general, all LP topologies will be equal to the product topology in the Hilbert cube. So yeah, that's why it's quite nice. And LP will be greater, contains LP minus 1. I'm just, guessing here, but yeah. So yes, nice problem. It took a long time, but yes, every single theorem and method that the book wanted us to learn would be taught very well here. So this problem teaches everything you need to know about the methods, pretty much. Right, now to end with a relatively easier problem. Hopefully, I actually solve it without pausing this time. This video probably has the record of the most amount of cuts. I don't think there's a single video which has these many, and probably part one, part two as well. Oh well. Yeah. So so before I show it's a metric, I'll just show that the D prime balls are contained in each other, right? So that should be good enough. So d prime is trivially, actually, I'm just going to directly use the constant definition. So d prime x comma y is always less than d of x comma y by assumption, because by the definition of d prime, right? And so what constant do we multiply by to get it? Hmm. Let's see. Hmm. Are they pausing again? Yeah, that's that. Okay. Yeah. So I just worked it out. I'm just going to explain what I did. So first, let's show that the equality inequality holds, right? So f of a plus b minus b minus f of b is less than or equal to f of a, right? So I couldn't actually use mean value theorem, but I solved it directly, and that also works. So skip all of this, yeah, from here on. So f of a plus b minus f of b is do some weird algebra and solve it, and here essentially it turns out to be this, and I'm just messing around with some properties from section 4, and you get this, right? So essentially 1 plus a is 1 upon 1 plus a is less than 1 upon 1 plus a plus b, because this is strictly positive, we're assuming that. And this is another less, it's another constant less than 1. So yeah, so we get f of a plus b minus f of b is less than equal to f of a from that. Now, on the other hand, we have the triangle inequality as it is for the regular metric. So yeah, we've already proven that. Oh right, I completely forgot. Yeah. So here I didn't realize that the constants didn't need to depend on. Were It was completely fine if the constants happen to depend on x and y. And because of that, if the constant happens to be say 2 plus 2d of, yeah, 1 by, yeah. If the constants happen to be, sorry, yeah, it's fine. Yeah, 2 plus 2 d of x comma y times d prime x comma y. So if I take this as t2, it's completely fine, right? Because it can depend on y. It can depend on this. So that's completely fine. Essentially, we got a bigger bubble. Yeah. So on to this. We're using the regular triangle inequality given to us from the metric, and then after flipping it, the inequality is flipped, but after adding the negative sign, the inequality changes again, and adding one changes does nothing to the inequality. But note that here we have f of a plus b, and we just proved it's less than or equal to f of a plus f of b. So yeah, this is less than or equal to d prime of x comma z plus d prime of z comma y. So yeah, sorry if it looks messy, but yeah, that's what I saw. So yeah, this was question 11, and it was a long journey, but quite enjoyable. All right, see ya.